I have many good memories of sitting around a fire on a starry night with a group of friends. The flames are dancing and I feel the heat warming my body. There have been stories told, songs performed, and marshmallows melted. There's something primal and meditative about watching and feeling this energy from the fire. It warms the skin and drives deep thought. But how is it happening? Why are we able to experience this energy? Why does a chemical reaction make this feeling so intense? Put another log in the fire and let's find out. This is Think 4. Early on in chemistry, you would have come across the terms exothermic, where heat energy is released, and endothermic, where heat energy is taken in. When wood burns in a fire, there is a combustion reaction, and heat is released to the surroundings, an exothermic reaction. Let's think about what is happening with the bonds in the molecules involved. We'll use methane, the gas we burn in a lab, as a simple example to work on. Methane contains one carbon bonded to 4 hydrogens. Each of these bonds has an energy associated with it, also known as the bond enthalpy. As you'll be aware, carbon to hydrogen bonds are very common and appear in all sorts of compounds. This means that the energy of this bond can vary depending on the environment it is in. Therefore, we use a value called the mean bond enthalpy, the average enthalpy for the CH bond. This can be found in your data book with a value of 412 kilojoules per mole. The energy required to break a methane molecule into gaseous carbon and hydrogen atoms can be calculated by multiplying 412 by 4, giving us 1648 kilojoules per mole. As this value was determined using the mean bond enthalpy, it will be an estimate of the energy required. For some molecules, we can obtain the exact energy required to break 1 mole of the bond into separate atoms. For example, diatomic molecules contain bonds that can only be found in one environment. For oxygen, O2, the bond enthalpy is 498 kilojoules per mole. Again, this can be found in your data book. Using bond enthalpies, we can determine the enthalpy change for a gas phase reaction. When combusting methane, 2 moles of oxygen are required and will form 1 mole of carbon dioxide and 2 moles of water. This is important as we need to include this in the enthalpy change calculation. In total, 2644 kilojoules per mole is required to break up our reactants. Using the same process, the total enthalpy of the products can be calculated. Just ensure that you include all the bonds involved. From the values in the databook, the total enthalpy is 3338 kilojoules per mole. It's important to note here that when the products are formed, energy is released. To show this, with the enthalpy value, we make it negative. To determine the enthalpy change, add the values together. 2644 plus the negative 3338 gives 694 kilojoules per mole. The result is negative, and so this tells us that it is an exothermic reaction. In the data book, you will also find the value for the enthalpy of combustion of methane, which is when 1 mole of methane burns completely in oxygen. This is the same reaction that we have been referring to, but the value calculated is different. This is due to it being a more accurate determination of the enthalpy change rather than using mean bond enthalpies. If you find yourself sitting around a fire with friends and you get stuck for a fireside story, then tell them about enthalpy change and appreciate how this exothermic reaction allows you to warm up when it's cold and perhaps, more importantly, to melt marshmallows. You never know, they might just be interested. This was Think 4. Thanks for watching.